Now, let's talk about second order reactions. And in second order reactions, it's either that the concentration or the rate of change in concentration of the product and reactant is dependent on the second power of the concentration of the single reactant or the first powers of both X and Y, the two reactants. Okay? So it's either there's one reactant with a second order of reaction, or there are actually two reactants, X and Y, that are both contributing at the first order of reaction to form the product, right? To form the change that we're seeing. Now, considering this, right? So let's first look in detail at this first one, right? Where two reactants are contributing equally as first order reactions to the reaction that we're observing. Right? Decrease in concentration of Y, right, is similar to decrease in concentration of X. Since both of them are moving at the first order reaction, we're going to see something more complex than that later on, but just for this time, right? Concentration of Y is changing the same way as concentration of X is changing. So we can just say, for example, that A minus, so let's assume that the change in concentration after a time T is X, right? So we can describe the concentration of both X and Y as, let's assume that the initial concentration of X was A. It can be described as A minus X at time T. And the initial concentration of Y as B, it can be described as B minus X at time T. Now, using that first formula again, right, as the concentration of X and Y change over time, this will be moderated by the rate constant of a second order reaction times the change in concentration of A over time and change in concentration of B over time. If we integrate this equation, we will now have Kt equal to 2.303 divided by A minus B multiplied by the log of B into A minus X divided by A into B minus X. Okay, if we rearrange this, we will be able to form a straight line graph again. Now, the reason why we keep talking about a straight line graph is because it's important. With a straight line graph, you will be able to calculate the rate of reaction. Okay, you'll be able to calculate your rate of reaction when you have a straight line graph. It's the easiest way to get into that. So once you have, you rearrange this equation, this is our integrated equation, into a straight line graph, which is Y equal to mx plus c, right? Of course, we know that our slope, right, is the m, which is, of course, here, once we are plotting time, we're plotting time, don't forget, we're plotting time against our, log A minus X over B minus X, which is our y-axis. Our x-axis is time. So our slope will definitely be A minus B over 2.303 times K. I hope you're following. And then our intercept will, of course, be log A over B. Okay? Now, that was a situation where two reactants were, two reactants were contributing equal rates of reaction to the final outcome that we have, right? So, for example, maybe co-administered drugs, right, that do not inhibit each other's forward reaction, and then you keep taking samples, over time, you will be able to have the first that we got. Now, let's assume that this drug, right, is it's this one drug that's contributing a double order of reaction, or a two order of reaction, a second order of reaction, right, where that same starting concentration is the same thing, since we're only looking at one reactant at this point. If we substitute here, right, and integrate, so if we substitute here, of course we'll have Ka here, right? Once we integrate that, we'll have Kt equal to X divided by A into A minus X. Of course, X is what the amount of the drug that has already been used up in the reaction. So that's the amount that has been used up divided by A, that's the initial concentration, into the remaining concentration, that's A minus X, okay? Now, if we rearrange this equation, we're going to get this. Kt is equal to 1, equation 15. Now, if the second order reaction is observed, then graph of this, 1 over this, right, versus time, right, the slope will give us K, and the intercept will be the inverse of the concentration at time t equal to 0. We also note that the second order of reaction is per concentration per time, and the SI unit is per mole per second, right? Half-life, if we do our input again, remember that at half-life, A has already degraded by 50%, so that'll be 100 minus 50. Once we input that into discuss. Hello? Hello? Is someone saying something? Do you have a question? Okay. So at 50% of the time, right, what we will have is T half is equal to 1 over AK. Okay, so this is the time it would take for the drug to have been eliminated, for half of the concentration of the drug that administered to have been eliminated by 50%. Okay, so very easy to just plug in your figures that you've been given and calculate from here.
Way in which drugs move through the body, through the body system.
Excellent. So it's